Hello, my name is John Jenkins and I'm a research associate at the University of Wales, Trinity St David. And today I'm going to be discussing the feasibility study titled A Low-Cost AI Defect Detection Solution for SMEs that, alongside my colleagues, I've been working on for the past 12 months. So to quickly introduce you to the study team, I was joined by a fellow research associate, Simon Thomas. Simon has a background in applied computing and specifically networking and cybersecurity. We also had inputs from Dr. Arno Maritin, who has a background in numerical methods, from Richard Morgan, the head of innovation and engagement, and Graham Howe, the head of the Made Cymru programme. So as well as our core team at the university, we were joined by contacts from our industrial partners at Highmark Automotive and Fiberx. To give you an overview of the motivations for our study then, we know that artificial intelligence is considered to be one of the fundamental enabling technologies of industrial digitalization, often referred to as Industry 4.0. Practical applications of narrow artificial intelligence are having a transformative impact across the manufacturing sector. However, there's a notable disparity with regards to the planned adoption of artificial intelligence between large enterprises and small and medium-sized enterprises. There is then, as a result, a significant risk of SMEs becoming the laggards of artificial intelligence due to these perceived barriers to adoption. And there's a clear need for collaboration or knowledge transfer between industry and academia to support digital technology adoption, particularly amongst small and medium-sized manufacturing enterprises. So to give you some insight to what's going on at our partner company, Fiberx. Fiberx is a manufacturer of injection molded components supplied to the automotive sector based in North Wales. They've recently developed a cobot cell to automate a glue deposition procedure for one of their main product lines. However, quality control remains to be highly manual and a fairly arduous process. We know then that the effectiveness of manual inspections is an extremely complex topic. So we have the combination of organizational, environmental, social, and psychophysical factors all influencing the effectiveness of a given procedure. And quality control activity is vital for determining process control at Fiberx, but also has the potential to bottleneck production. As such then, this necessitated the development of an automated inspection procedure. So what are the challenges of developing such a system? Well, glue bead defects rarely occur with a high degree of visual similarity, and that poses us a pretty significant headache in automated defect detection. Conventional approaches would rely on the development of numerous handcrafted feature extraction algorithms for each defect type, which can quickly become an exceedingly complex task. Deep learning in the form of convolutional neural networks offer us a plausible solution here, but would typically require thousands of labeled training images per class to achieve reliable performance, which again can become extremely costly. And defects are, hopefully at least, a rare occurrence, leading to a paucity of available training data on which to build our models. So all of these challenges then led us to two research questions. Can Siamese neural networks challenge the data availability problem in automated defect detection and thus reliably identify glue bead defects? And can these Siamese neural network models be deployed using low-cost edge computing devices? So the methodology that we use throughout the study can be broken down into sort of six main pillars. We developed the proof of concept hardware using low-cost devices. We compiled a training data set from 20 product samples collected by our colleagues at Fiberx. We labeled the ground truth for that training data set using the existing quality control criteria as defined by Fiberx. We defined our model architecture for this binary classification task, which I'll discuss more in a moment. We trained that model and performed some hyperparameter tuning to optimize its performance. And finally, we performed K4 cross-validation and some inference testing on our edge computing devices to sort of validate or test our model, and the results of which I'll present in a moment. Okay, so utilizing low-cost, commercially available solutions and open source software for image acquisition and processing was fundamental to our study's low-cost objectives. So in terms of acquisition hardware, we used standard CMOS type sensors with CSI or HDMI interface. And we also, in terms of our processing hardware, we used a low-cost single-board computer called an NVIDIA Jetson Nano. So the combined cost of our image acquisition and processing hardware was kept below £150. Next, we had to compile our training data set. So we gathered around 100 images per class, the classes being defective and non-defective, from around 20 product samples supplied by Fiberx. And then we labeled the ground truth as to whether each of those images represented a defective or non-defective example, using the existing quality control criteria as defined by Fiberx, our partner company. And it's worth mentioning here that the pairwise learning that can be achieved using Siamese neural networks can significantly increase dataset size. So instead of having only say 100 images per class for each discrete class, we have a significantly larger number of unique combinations of defective and non-defective pairs that we can use to train our model. And the images shown there are just some visualizations of some similar and dissimilar pairs, and the minimal pre-processing and augmentation steps that were taken before we commenced training of our model. So the Siamese neural network model that we used or deployed in this study is comprised of two 13-layer sub-convolutional neural networks and was first developed by Koch et al. In 2015. So a major benefit afforded to us by the use of Siamese neural networks is that by comparing image similarity to our nominal state, our non-defective state, rather than assigning images to discrete classes, as we may do in a more conventional convolutional neural network-based classification model, we can detect new defect types without retraining the model. So we can detect defect types that weren't included in our training data without having to retrain our model. So some plots from our model training, and I won't bore you with too much detail here, but what we're essentially looking for is signs of overfitting or underfitting. So in this case, we're making sure that the graphs presented on the bottom in terms of validation loss and validation accuracy closely mimic the sort of behavior exhibited in the graphs on the top, which are training loss and our training accuracy. And we can see in this case, they do closely follow or mimic that behavior. And the model was developed on a standard NVIDIA 3080 Ti desktop GPU prior to deployment on the NVIDIA Jetson Nano edge device. The model performance was evaluated using k-fold cross-validation with k equals 5. We chose k equals 5 as a sort of split. Our train test split was around 80-20. And k-fold cross-validation is particularly useful to us when using limited data sets, as it allows us to test and train the model across the entire data set, rather than having discrete groups for training and for testing. And we can see our sort of detection accuracy peaked in fold 1 at 97.6%, but our mean detection accuracy was around 95.28%. And there's a visualization of the output of the model on the right-hand side of the screen. So what does all of this mean? It means that if we pass defective and non-defective images into our model, we can distinguish or classify them with a high degree of certainty. The next step in our methodology was inference testing, so testing our model on our edge computing devices. So some more defective product samples were collected by our partners at Fiberx. And from those samples, another testing dataset was generated containing approximately 50 images per class. So the model was then deployed on the NVIDIA Jetson Nano using TensorRT via the Open Neural Network Exchange framework. And whilst deployed on the edge computing device, we achieved a defect detection accuracy of 95% across 100 observations, with a mean inference time of around 122 milliseconds, or around 8 frames per second, which means we have a real-time application or a real-time system here, but there's still some room for optimization to improve that frame rate. So some of the ongoing and future work, we're working with Fiberx to develop discrete event and 3D process simulation models to determine the impact of this inspection routine on the current process cycle times. We're looking to test and deploy the inspection procedure within the cobot cell at Fiberx in the very near future. And we're investigating optimization strategies to improve the runtime performance on our edge computing device, the NVIDIA Jetson Nano. And some upcoming opportunities for dissemination of the findings of our study. We're working to develop a technology adoption case study. We look to present the findings of that at the Made Cymru Industry Summit in June. And also, we have the Smart Digital Accelerator project. So the Smart Digital Accelerator project is a Welsh Government funded project delivered by the University of Wales Trinity St David's in collaboration with AMRC Cymru. And it looks to, it aims to support local or Welsh manufacturers in the adoption of digital technologies within their operations. So just to summarize and come back to those two research questions that I presented at the very start. Using Siamese neural networks to challenge the data paucity problem in defect detection is feasible. And we know that Siamese neural network models can be effectively deployed on low-cost edge computing devices. However, there's some work remaining in terms of optimizing these models to improve runtime performance. And to give you an overview of some of the outcomes of this feasibility study. Myself and Simon have secured research associate positions at UWTSD, and we're both commencing PhD study as a direct result of that later on this year. We've developed a really strong sort of collaborative relationship with our industrial partners at Fiberx, and we're seeking to continue engagement through smart partnerships and potentially KTPs. And as we said, we're working with Fiberx to develop this low-cost digitalization case study using the findings of our feasibility study. Thank you very much for your attention during this presentation. And if you have any questions, please get in touch via my email j.jenkins@uwtsd.ac.uk. Thank you.